So let's look at some examples, or an example of a binary operation. So let phi be the map from z squared, that is the Cartesian product of the set of integers with itself, into the set of integers, and let this function be defined by phi of the ordered pair AB is the sum A plus B. Then, if we add any two integers, we once again have an integer. And so this function, phi, is a binary operation. On the set of integers. So next we will look at an operation that is not a binary operation. So let phi be the map from the Cartesian product of the set of integers modulo 2 with itself into the set, which is the union of the set of integers modulo 2 with the singleton set containing the number 2. And so let this function be defined by phi of the ordered pair AB is the sum A plus B. Then we look at adding the elements in the set of integers modulo 2. 0 plus 0 is 0. This is an integer modulo 2. 0 plus 1 is the same as 1 plus 0, which is 1, which is once again in the set of integers modulo 2. But 1 plus 1 is the number 2, which is not in the set of integers modulo 2. And so the range of this function, phi, is the union of the set of integers modulo 2 with the singleton set containing the number 2, and this union is the set which contains the numbers 0, 1, and 2, which are the sums for the elements in the set of integers modulo 2. And so the function phi, as defined, is an operation. It is something that we do to the elements, in this case 2 elements, in the set of positive integers, that in this case produces an element which is not in the set of positive integers. And so phi is an operation, but is not a binary operation on the set of integers modulo 2, since it produces elements in the union of the set of integers modulo 2 with the singleton containing the number 2, which is not a subset of the set of integers modulo 2. So as an exercise, let the function phi have the domain of the Cartesian product of the set of positive integers with itself, and let this function be defined by phi of the ordered pair AB is the difference A minus B. First, determine the range of this function, and second, answer the question, is the function phi a binary operation? On the set of integers, correction, the set of positive integers. So a set is of little practical use on its own. So we consider structures formed on sets Now, in general, there are three classes of structures. And those are algebraic structures, analytical structures, which we sometimes call differential structures, and topological structures. Now we will begin by looking at some algebraic structures, and later we'll look at some analytical and topological structures. Now, roughly speaking, an algebraic structure consists of one or more sets together with operations defined on those sets and the first algebraic structure that we'll consider is called a binary algebraic structure. A binary algebraic structure consists of a single underlying set together with a single finitary operation defined on the set. Now, the word finitary means that the operation takes as an argument a finite number of elements in the set. We have already looked at two such operations. One is a unary operation. And in a unary operation, a given set is mapped back into itself. In terms of elements from the set A, we have a single element being mapped into a single element, which is once again in the set A. We have also looked at binary operations. In this case, we have a Cartesian product of the set A being mapped into the set A. And in terms of elements, we're looking at mapping an ordered pair of elements, which we'll call A1 and A2, into a single element, which is once again in the set A. Now, in general, we have operations called in-ary operations, and in this case we are mapping a superscript n into the set A, and in terms of the elements, we have an ordered n tuple, that is a ordered set of n elements from the set A, so a sub 1 through a sub n, and this object is mapped into a single element in the set A. So let's look at a specific binary algebraic structure. So new definition, a set M together with a binary operation, which we will denote with the abstract symbol star, defined on the set M, is called a magma. It is denoted using angular brackets, and grouping the set M together with the binary operation star defined on the set M. Now, I will follow the convention that for algebraic structures I will use angular brackets. In general, I'll use parentheses for spaces, but some algebraic structures are spaces, and so there's some crossover. But in general, if I use angular brackets, I'm referring specifically to an algebraic structure. Okay, so notice that a magma is a binary algebraic structure where the operation, the finitary operation, is a binary operation. If a set is closed under a specific binary operation, we say that the set is a magma under that operation, and notice that the properties of a magma depend on both the underlying set and the specific operation. So let the set M together with the binary operation star be a magma. Notice that if A and B are two distinct elements, or any two elements, not necessarily distinct, in the set M, then A star B is an element in the set M, and B star A is an element in the set M. Since the set is closed under the binary operation star, when we perform the operation with the elements A and B, in whichever order, that produces an element which is once again in the set M. However, it is not necessarily true that A star B is the same element as B star A. Similarly, if A, B, and C are any three elements in the set M, then A star, the quantity, B star C, is an element in the set M, where B star C is an element, and so we are once again combining two elements. And the quantity A star B star C is an element in the set M, where here we're combining an element which happens to be A star B with the element C. So both these elements are in the set M. The result of performing the operation this way is an element in the set M. However, or but, it is not necessarily true. That these two elements are the same. Further, if A star B happens to be equal to A star C, this does not imply that B is the same as C. And if B star A happens to be the same as C star A, this does not imply that B is equal to C. Okay, so we will end here for today. Next time, we will look at specific types of magmas that satisfy additional properties other than closure. And we will begin the next lecture by looking at the solution of the exercises that were set in this lecture. So I hope you have enjoyed the first lecture. Thanks for watching.